Okay, so let's talk about the Doppler effect. Anytime you've ever heard a siren go by, you've had personal experience with the Doppler effect. It's simply a phenomenon that we see when the observed frequency of an emitted wave is different from the frequency at which it was emitted from its source. This happens because there's relative motion between the observer and the source of the wave. Now, this could be the observer moving towards the source or away from the source. This could be the source of the wave moving towards or away from the observer. If you're standing on the side of the street and the siren comes screaming down the street, it's moving towards you at first. And so as it's moving towards you, you're going to observe an increase in the frequency from what it's emitted at. Once it goes past you, and as it's close to moving past you is when you probably notice the most change. But once it's gone past you and it's driving away, if you listen closely, you'll notice that the frequency is actually lower as it moves away, and this is because of the Doppler effect. And as we just mentioned, we see that if the source is moving towards the receiver or the receiver towards the source, then we get an increase in the frequency. If the relative motion is away from the receiver, then the observed frequency is lower. And so if we take a little bit closer look at this, if there's no motion, then in this case we'll talk about a siren on a train. Let's say it emits a siren, it emits a tone at 40 hertz. 40 waves per second leave the siren, 40 waves per second enter the source. If we look at the back end, remember that sound generally gets emitted in all directions. We have 40 waves per second moving in this direction. The observer is our guy back here. 40 waves per second enter his eardrums, and so he hears a 40 hertz tone. Now, on the other hand, if there's motion, the siren is still going to emit its same 40 hertz per second. Gives it some wavelength. But if the train is moving, in this case we'll say to the right, at some velocity, as it's emitting those waves, it's also moving in the same direction as those waves. And so each successive wave front is not emitted in the same place. It's emitted closer to the one that was just emitted. So what that does is it causes the wave fronts to pile up, and it causes the wavelengths to get shorter. And when we have shorter wavelengths, as the wavelength goes down, that increases the frequency. Wavelength goes down, frequency goes up. We observe a higher frequency. We observe more waves per second, which is a higher tone, a higher pitched tone. Now again, if we look at the back end, okay, again, we have 40 hertz being emitted. The waves are moving in this direction. The train itself is moving in this direction. And what that does is it stretches out the wave fronts. Each successive wave is emitted further away from the wavelength that was just emitted. So instead of being the same distance between them, now they're getting stretched out. So this is actually increasing the wavelength, and we know from previous lessons that if we increase the wavelength, we decrease the old frequency, and that gives us that lower tone. So if they're moving towards us, that gives us that higher tone. If they're moving away from us, that gives us a lower tone. How's that? Does that help? Or does it just scare you? I apologize if it does the latter. And we'll talk about it in a little bit, but it actually does the same thing for light. The speeds just need to be greater. Now, the actual mathematical equation for this looks like this. It's f prime equals f plus or minus v, or v plus or minus v sub d divided by v plus or minus v sub s. And in this case, f prime is the observed frequency. It's what you hear. It's what is recorded. F is the original frequency. It's the frequency of the emitted wave. V is the speed of the wave normally in that particular medium. So if we're talking about sound and air, this V would be 343 meters per second. If we're talking about it in some other similar temperature, similar substance, obviously that's going to change. V sub D is the detector. It's the observer. It's the thing that's hearing the sound. And then V sub S here is the source. It's the thing that's producing the sound or the wave, whatever it happens to be. Okay, so there's a lot of stuff going on here, but once you understand what the equation is telling you, it's really quite simple to use. And so let's look at a couple different examples. The first one would be if the source, let's go back to this one, source moving. Alright, so it stopped recording for a moment, and I'm not entirely sure how long, so we're going to backtrack a little bit. Quick recap, and I apologize if we already said this. This expression right here, v plus or minus v sub d over v plus or minus v sub s, that's our shift. That tells us how much it shifts. If the frequency is shifting up, that expression v plus or minus vd over v plus or minus vs should be greater than 1. If it's shifting down, that expression needs to be less than 1. So if we have a source moving towards the detector is not moving, so it has a velocity of 0 meters per second. In order to get that shift up, the denominator needs to be smaller, and so we're going to have v minus vs. Whoops, didn't mean to do that. If we have the if we have the source moving away, that's going to give us a shift down. And so the perceived tone or the heard tone is going to be lower than what is emitted. And so the v over v plus or minus vs has to be less than 1. So that means it'll be v or f times v over v, and then to make the denominator bigger, we're going to have to add. So there's our source moving away. Now, and in that case, let's see if we can move this. There we go. Okay, so now we have the source moving towards the detector. So here, our detector has a, we're talking about the detector moving now. Whew. Where's our eraser? There we go. Can't do that. Okay. So our detector is moving towards the source. And so our source has a velocity of 0. If the detector is moving towards the source, again, f equals f prime. Our source is going to be 0, so it's v plus or minus v sub d over just v, because vs is 0. So now if we're going to shift up, Again, that means our expression here has to be greater than 1, and so for that to be greater than 1, we're going to add v plus v sub d. So it'll be v plus v sub d over v. That's if the detector is moving towards the source. If we got two things going on here now. There we go. And let's move that up there. Nice. Now, if the detector is moving away from the source, that's going to give us a shift down. Okay, so that means we're going to have a lower frequency. So our expression here has to be less than 1. In order to get that to happen, our numerator needs to be smaller than the denominator. So it's going to be f prime v minus v sub d over v. Now, don't just go and try and memorize all 4 of these relationships. Understand how the equation works. Understand the application of the equation. What is the equation telling you? What is the scenario? What's going on? Is it being shifted up or down? What's moving? How do you get that shift to happen? If there's movement, if there's relative movement, so the source and the detector are moving away from each other, that's going to shift the sound down. If they're moving towards each other, that's going to shift the sound up. I don't know if that helped. It may just give you nightmares. I apologize. Just trying to illustrate the point. So the source is not moving. If the detector is moving, then that's going to be a slightly different scenario. So that's what we just. This example is it's how the Doppler effect was measured. Our scientist Christoph Bois-Belot actually got a train and attached a flat car to it and put musicians on the flat car that were exceptional musicians and could play specific notes with extreme accuracy. And so then he had the train drive towards and drive away from scientists who were listening to those tones and measuring those tones and could actually tell and could measure the differences. I'll leave that to you to actually calculate, and you can check and see if you got the right answer with your teacher next class. But just like any of our other wave phenomena, the Doppler effect is not something that's specific for one type of wave. It applies to all different types of waves. Not just sound, not just waves in a string, waves in a puddle, whatever. It also applies to light waves, and so in all electromagnetic waves, really. Electromagnetic waves can undergo this Doppler effect as well, and has been measured. And reading the bumper sticker, it's pretty funny. If you get it, great. If not, let's talk about what it means. Okay, so if we have light, and keep in mind our equation for the Doppler effect. It takes into account not only the speed of the observer and the detector, but also the speed of the wave itself. And so sound, roughly 343 meters per second. Light, roughly 3 times 10 to the 8th meters per second. And so notice that significant difference in speed of the actual waves means that in order for a noticeable difference, a noticeable shift, there has to be a much, much larger relative velocity. So the things emitting the light or the things detecting the light have to be moving much, much faster to get any type of shift. And if we think about what we know about the electromagnetic spectrum, which is just a name, really, for a range of radiation, let's talk about visible light. Why not? the longest wavelengths in visible light occur in the red wavelengths, or in the red color area. The highest frequency, lowest wavelengths, so over here we have high frequency, low wavelength. Over here we have, and again relatively of course, lower frequency, higher wavelength. And thinking about how the shift occurs, if you're moving, the relative motion is away from the source or away from the detector, that shifts the frequency down. Well, in sound, that gives you a lower tone, but in light, it gives you a redder tone or an oranger tone. And if the relative motion is towards the source or towards the detector, when we're talking about sound, that gives you a higher tone. Whereas if you're talking about light, that higher frequency relates to red light, or blue light or purple light, indigo light even. And this idea of the Doppler effect for light and the observation of the Doppler effect, specifically the red shift of light from other galaxies, was one of the first real hard pieces of evidence for the expansion of the universe. It's one of the ways that scientists were able to definitively show that our universe was actually expanding, because that light from the other galaxies and from stars was being shifted towards the red end of the spectrum. So there's your Doppler effect. Have a good night.